Hi, my name is Raychel Nelson. I'm a senior in atmospheric science, and I'm an undergraduate research assistant in the Weather Radar Research Lab at Purdue University. I have been conducting this research project since June of 2020 with the help of my research advisor, Dr. Robin Tanamachi. The goal of this study is the utilization of the X-band Teaching and Research Radar, or EXTRA, installed near campus in 2018 to automatically detect mesocyclones, particularly in the low levels. The Purdue University campus is located about 70 kilometers northwest of the nearest National Weather Service WSR-88D radar, meaning that even at its lowest elevation angle, the beams pass over Purdue's campus at approximately 1.2 kilometers above ground level and higher, shown in Figure 1. This leaves a significant portion of the lower atmosphere unscanned, creating a blind spot where dangerous or otherwise important meteorological phenomena may develop. In such cases, using the data from the radar in our own backyard can be quite beneficial. We hypothesize that low-level mesocyclones within EXTRA's 50-kilometer range can be algorithmically identified in EXTRA observations faster and with higher resolution than in observations from the nearest WSR-88D to the mesocyclone. The team studying the EXTRA and its output does not currently have all of the algorithms the National Weather Service uses with their radar data to issue warnings and watches. So studies like these seek to develop those programs for use by that team so that they may use their own radar data and analysis to supplement the watches and warnings issued by the National Weather Service for our campus. In this work, we aim to write a Python program that uses extra data to automatically identify mesocyclones. To accomplish this, we used radar data files from past local storm events that were known to produce at least one mesocyclone within the EXTRA's domain and passed them through the algorithm. This study utilized a storm event from May 27, 2019, analyzing the hour of 23Z or 7 p.m. local time. The example calculations and plots shown here are from one data file scanned at 3.1 degrees, about 2.5 kilometers above ground level at 45 kilometers from the radar, where the mesocyclone of interest lies, at 2330Z. As shown in Figure 2, the program plots the reflectivity, 2A, and velocity, 2B, of the storm. The linear least squares derivative method was used to calculate azimuthal Doppler velocity shear, or the change in wind velocity as the radar changes azimuth when sweeping around its domain. 2C displays this outcome while 2D shows the area of the radar gate covered by azimuthal shear values equal to and over a chosen threshold of 0.005 Hz. These calculations were repeated for the 186 radar data files from this storm over 15 elevation angles and about 1 hour. By compiling the calculations from all the files and producing scatter plots like the ones in Figure 3, we can see the area covered by regions of relatively high azimuthal shear at each elevation angle over time. Only a selection of angles are displayed here for readability. Figure 3a shows the area covered by azimuthal shear values equal to and over 0.0025 Hz, while Figure 3b shows values equal to and over 0.005 Hz. These show that the mesocyclone in the May 27, 2019 storm first developed in the low and mid-levels before ascending to higher elevations. Making plots for different thresholds will allow us to determine the right parameters to code into the algorithm to detect future mesocyclones accurately. After identifying the mesocyclone in extra data, the next step was to determine whether this mesocyclone was also detected by a WSR-88D. Radar data for May 17th was sourced from the NOAA NextRad Radar Data Archive and visualized using the NOAA Weather and Climate Toolkit. Comparing velocity signatures between 4A and B, it is evident that the mesocyclone identified by KIND, marked as 435, matches the location of the velocity signature associated with the mesocyclone detected by this algorithm. It is important to note that the aerial coverage of high azimuthal shear depicted in Figure 3 is for all areas within the radar's domain above that threshold. Ideally, only the area covered by the mesocyclone of interest would be depicted. In future work, we plan to use one of several possible tracking algorithms to identify both storm objects and azimuthal shear objects that can then be correlated in order to determine the most likely location, size, and track of any mesocyclones. Future plans for this study also include comparing parameters of mesocyclones detected between radars, such as strength and time detected, to determine the validity of the hypothesis. I would like to thank the Purdue University Department of Earth, Atmospheric, and Planetary Sciences for funding this work. I'd also like to credit the Python ARM Radar Toolkit for figure generation and the NOAA NextRad Archive for KIND radar data. Thank you so much for having a look.